Hello, and welcome to Module 1 for Mechanics of Materials, where we talk about how external loads equal internal stresses. In this lecture, we're going to be focusing on normal and shear stresses, what they are, and axial and torsional applied loads to members. I'm Dr. Kate Frisch, and this is Mechanics of Materials. We're going to be focusing on developing an understanding that all external loads create mathematically predictable internal stresses that are either normal or shear. Along the way, we're going to develop knowledge or learn that the difference between normal and shear stresses, so pull apart versus sliding mechanisms, the types of stresses created in axial and torsional members, the formulas for normal and shear stress due to axial and torsional loading, and the safety factor formula. So maybe you're like Calvin in this Calvin and Hobbes cartoon. Have you ever wondered how they know the load limit on bridges? Hopefully someday you'll have an opportunity to answer that question for a curious 6-year-old. And you'll have a better answer than Calvin's dad does. That's what we're going to be talking about today, setting us on a road to have a better answer than that. So it's Play-Doh time. The first thing I want you to do is pull out your Play-Doh and make 2 cylinders that have equal heights and different diameters, and place them on end like they're shown in this picture. Then I want you to take something that will cover the top of each cylinder, place it on the top of each cylinder, try not to squish the cylinder completely flat, choose your weight carefully, and observe what happens when you place the same weight on each cylinder. You don't need to do this simultaneously, one at a time. So what do you notice? You probably notice that they squish, but hopefully you notice that they squished different amounts. The change in length of the cylinder is different. And that means that different areas respond differently to the same force. That means that the forces that you learned how to find in statics and dynamics aren't enough to predict how a material is going to respond when it's loaded. And in order to determine whether or not something is going to fail, we need to know how the material is going to respond. So we have this concept of stress. Stress describes the intensity of the force, and it takes into account the difference in area. So normal stress, which we represent with the Greek letter sigma at the top there, describes the force perpendicular to the surface relative to the area. So you see in the right the force and the area, and mathematically, it's defined as the limit as the area gets smaller and smaller and smaller as it goes to 0 of the force applied to that area. Functionally, for average normal stress, this simplifies to sigma equals force over area. Stress is force divided by the area for the normal stress. And it has units of force over area, newtons per meter squared, so a derived unit called a Pascal, which you may have seen when you've talked about fluid pressure in physics in the past, or pounds per inch squared, which in English units frequently gets abbreviated as PSI. The shear stress, which we represent with the Greek letter tau, describes the force parallel to the surface, and similar to the normal stress is defined as a limit. But there's 2 forces here. There's the one along the x-axis, and there's the one along the y-axis in the figure shown. So shear on the in the z direction along the x-axis, tau zx, is the limit of the force in the x direction over that area, and shear along the y direction, or due to the force in the y direction, in the z direction is described based on the force in the y direction. For an average normal stress, this simplifies to the shear force, V, divided by the area. So tau, the shear stress, is equal to shear force divided by the area it's applied over. Again, this has units of force per area, so pascals or psi, depending on your unit system. So here's a question. Can you add normal and shear stress? I'm going to give you 30 seconds to pause and think about that question. I want you to think about why or why not. And the answer is no. You can't add normal and shear stress. They're two different kinds of stress. They are both stress, but they have different fundamental mechanisms, as we saw in some of the early work we did with Plato in class, where shear is twist apart stress, where you make the molecules slide past each other, and normal stress is pull apart stress. So you're trying to break the bonds by pulling them. So you can't add them together, which leads to some questions like, well, how do you deal with a situation where you have both normal and shear stress? How do I know how it's going to fail? And there are ways to do that, and we'll talk about that towards the end of this class. But they do not add together. They are different failure mechanisms, so you don't mathematically add them like vectors. So now we're going to talk about a special case that causes shear stress, and that is twisting. So to think about this, I want you to take your Play-Doh cylinder, make another cylinder, and scratch a line on the flat end. So down here on the flat end. You can also scratch one of the lines shown here if you want. Then I want you to take it with both hands and I want you to twist it. And then I want you to notice what happened to the lines. The circular lines around the Play-Doh that are drawn here that I didn't ask you to do remain circular. The longitudinal lines become twisted, and the radial line on the end of your Play-Doh remained straight. But you'll notice that different places on the Play-Doh, on this radial line, twisted more than others. So there's no twist here at the center of the shaft, and there's the most twist at the end of the shaft. And that's going to be important as we start to think about how shear stress occurs due to the applied torque for twisting. So shear stress due to twisting, when you apply a torque about the axis as shown there, using the right-hand rule, that's a counterclockwise torque or a positive torque about the axis along the center of the beam. You'll notice that the maximum shear stress is going to occur at the edge of the beam because that's where it deflected the most. But anywhere between the center and the edge can be modeled as a ratio of the radius at the point you're interested in, rho, versus the radius at the maximum edge of the shaft, c. So if you think about the torque applied, you define that mathematically, relate the stress to the torque, and substitute in that relationship for the relative torque that we just talked about. And remember that the maximum torque over the radius of the shaft is constant. You get an expression for the torque that depends on the maximum torque, the radius of the shaft, and this integral over the area of rho, the radius at the point you're looking at, with respect to the area. So we're going to call that integral piece J, which we'll talk about more. J is something called the polar moment of inertia, which you may have seen in your statics course. And it is defined as the integral of the radius with respect to area. So you can do the math to do this integral, integrating from 0 to c, doing a substitution to get this is for a circular, solid circular cross section. And this evaluates to pi over 2 times c to the fourth. Okay, that's the polar moment of inertia for a solid circular cross section twisting about the axis out of the page. Okay, it's for a solid cylinder. Now, that's one particular case. There are many cases. Engineers have typically done these calculations for the variety of cases that exist, and you can look them up in a table in your textbook for a lot of common cases. So hollow cylinders, square, rectangular cross sections, those kinds of things. And we'll be using that table quite a lot as we talk about twist and shear stress due to twisting. So now that we've defined the polar moment of inertia, J, first there, we're going to go back to that formula that we had And note that the maximum shear stress, this is rearranging it just a little bit, is equal to the torque times the radius of the pipe divided by the moment of inertia. Okay, so and that will work regardless of what cross-section you have, because J is something that changes based on cross-section, and you can go and calculate the right J for your cross-section. So that's the maximum torque. At any point, you can figure out what the torque is by, instead of using C, the maximum radius, the extreme fiber of your object, of your cross-section, you can use rho. But it's important to note with this that the direction of your shear force varies as you go around the pipe. It's always perpendicular, as shown in the figure there. So that's going to matter when we start to talk about adding and directions later in the course. One more thing that I want to talk about here, common use of shafts is for power transmission between motors. So a motor will typically be rated for some horsepower, like a 5 horsepower motor, and that means that it delivers a particular torque at a given frequency, operating frequency. And motor suppliers, typically at least for electric motors, supply these sorts of curves where they give you the power of the motor and the output velocity, angular velocity, so that you can estimate the torque that your motor can supply. So one of the things you'll see in some of the problems that we do is that saying you have a 5 horsepower motor, it's operating at 180 revolutions per minute, and then go in and ask you for a shear stress. So you're looking to think about what's the torque. When you hear that information, those specifications for a motor, you're asking to think about what's the torque. And note that this frequency right here is in radians per second. So if you got motor specifications like I just said in revolutions per minute, you're going to need to do the math to get yourself to radians per second. So back to this question, will it break? We haven't really talked through all of the ins and outs of this yet. We will be spending a lot of time working towards an understanding that allows us to answer this question well, because your engineering supervisor is not going to be satisfied with Calvin's dad's answer. But one of the tools that's an important predictor in this is something called the factor of safety, or sometimes in the Hibbler textbook it's called allowable stress. The factor of safety is defined as the actual stress divided by the allowable stress. So the allowable stress is based on the material properties. So often, but not always, sigma allowable stress is equal to the yield stress for the material, if you remember from from material science. And the actual stress is whatever you calculated based on your loading. So we'll be working with this idea in class. The shear stress equation looks just the same as this, except you replace the sigmas with taus. So we'll be working with this idea. So with that, I'm going to let you switch over to some videos where you watch examples of problem solving, and I will see you in discussion, and we will try this out.